Welcome to the second lecture for CS2106. Can you hear me? Can you hear me? Okay. All right. So let me start with some administrative matters. All right. I received emails about issues with tutorial slots and lab slots and so on. Right? In general, I am flexible in terms of which slots you attend, as long as there are enough seats in the room and in the lab. Okay. Now, if you want your lab slots, you want to change your lab slots and you want it to be sort of formalized through the course systems, you can either appeal through course, or you can email the two TAs that is helping with registration issues, and these are their names and their email IDs. Okay. So basically, you email them with this email ID at com.nus.edu.sg. Okay. So this is if you have any issues with the lab and tutorial registrations. Now, the tutorials and the labs will start next week. Right? The lab sheets and the tutorial sheet will be posted by tonight. Okay, so watch out for updates to the blogs. So this will be posted onto the blog for you. Now, let me talk a little bit more about Lab 1. Now, Lab 1 is the purpose of Lab 1 is to get you warm up, and get familiarized with the Unix environment, and also doing C programming on Unix. Okay? So it is an ungraded exercise. If you are not familiar with Unix and C, you are highly encouraged to follow through this exercise, even though it is not graded. Okay? Now, whatever you learn from the exercise will help you later in the later labs. So if you skip this lab, you are going to have trouble with your future labs. That one I'm pretty sure. Okay. So please follow through. Make sure you learn whatever things that is mentioned in the labs, whatever commands that we want to teach you, so that you can save your time. You can save yourself some time and loss of hair and things like that over the semester. Okay. So please do that, even though it is an ungraded exercise. Now, the lab location, for those of you who do not know, it is Com1 basement. So if you go to Com1 basement, you go down the stairs, it will be the first one, I think the first or second one on the right. It is near the study area of the basement. Right? And the name of the lab is IT Security and OS Lab. All of you should have access to the lab, right? Now, once you register for the class, you should automatically have access to go into the lab. If you have trouble using your metric card to enter the lab, please approach the help desk, right, so that they can set your metric card access properly. Okay, so this is about the lab location. Now, for the first lab and several other subsequent labs, you will need a School of Computing Unix account, right, so that you can log on to our Unix servers to work on the lab assignment. If you do not have such an account, for example, if you are from a different faculty or you're exchange students, you can go online to this URL here to apply for an account. Okay. So you need that for your lab 1. Okay, any questions about the lab and tutorials or any other administrative matters? Okay, so let me continue. So at this point, I would like to introduce to you our teaching team. Okay? So we have a team of students that is assisting me in conducting the class, including tutorials and labs. Okay? So let me start by introducing you to Fang Chen Fang, who is our TA. So can you come down and maybe say a few words about yourself?
Yeah, good afternoon. Welcome to CS2106. I'm Chen Fang. I'm going to assist in tutorial teaching.
And you are a PhD student?
Yeah.
Which year?
I'm year 4 PhD student.
Year 4 PhD student doing security. So we have a security expert who needs to know a lot about OS in order to do security. And next we have labs, teaching lab staff. So we have 6 of them. Let me start with Hofan.
Hello everyone, I'm Zhou Hufeng from Computational Biology Lab. I'm in the 3rd year. Third year PhD student. I hope I can be as good in the eyes of my students as my teachers in my opinion.
Right, thank you. And Hufeng will be taking care of, I think, all 4 labs on Thursday. So if your lab is on Thursday, he will be there to take care of you. Okay. And then let me now go through. Okay, maybe Chen Zhe.
Hello, I'm Chen Zhe. I'm also 3rd year, but I'm undergraduate. Okay, I learned this module last year, so I got a first-hand experience. This module is very interesting, and the professor is also very responsible in teaching. But some of the labs you will find a bit challenging, and that's why you need us. Don't hesitate to ask us questions. That's all.
Hello everyone, I'm Liu Liu, undergraduate year 3 student, and I took this class last year and I'm enjoying very much, especially the labs. You will know what I mean later. So feel free to ask me questions, otherwise our lab TA will be very bored. Hope you enjoy the class.
Alright, thank you. Do you have Yongzhou here? Yongzhou Tan? I saw you just now. Okay, can you come down? And Saranya, are you here? Okay, that's it.
Hi everyone, my name is Tan. And I took this, I'm also year 3 and I took this module last year. I hope everyone will have a good time with the lab. I hope everyone will have a good time with the labs. And I hope everyone will learn a lot of things from the lab. I enjoyed the lab very much and I hope everyone will do it. So thank you very much.
Right, thank you. Right, so some of the, as you heard, some of the lab TA this year are from students last year. And so they can share their experience, their tricks that they don't want me to know, for example, how to do it in the labs and so on with you. Okay, right. So we have 2 more, Xian Yongzhou and Saranya Sekar, who are not here today, but I'm sure you will meet them in the lab sessions. All right. So thank you. Okay. So now I will start the lecture for today. So today is still going to be an introductory lecture. Right? We are not going into details as yet for today. Okay. We have 2 halves of the lecture. The first one, I'm going to give an overview of the different abstractions and interfaces provided by the operating systems. And in the second half, as I promised last week, I'm going to give a brief introduction to C programming, assuming that you already know Java. Okay. Now, for those of you who are already familiar with C programming, feel free to skip the second half. But if you want to stay, you're most welcome to stay as well. Okay. So let's start with the first half, where I'm going to talk about the abstractions and interfaces provided by the operating systems. Okay. So let me start with the first abstractions or concepts that is available in the operating system. It's called a process. It's a process. Now, before I explain what is a process, let's briefly review what is time sharing. Okay. Now, time sharing means that you have multiple tasks running on the computer systems. Maybe it is from one user, maybe it is from multiple users. Right? But in order to appear to the users that all of these programs are running at the same time, even though you have only one CPU, right? The operating system have to switch between running these different tasks very frequently. Okay, so let's say that I have one task 1 over here that is currently running, and when a task is running, it is running on the CPU. It has some data and code stored in the memory. It might be reading and writing to the disk, right? It might be sending and receiving data over the network. Okay, so I have a task running. Now, in the meantime, there might be other tasks that is ready to run, or has run but has been suspended, and they are waiting in a so-called, I just call it waiting area. It's not a technical term. Right? They are just waiting there, waiting for their turns to be run by the operating system. Now, after some time, the CPU can switch. Maybe you want to switch from task 1 to task 2, right? And then it switch from task 2 to task 3, and then task 3 to task 4, maybe task 3 back to task 1 again. And then this can repeat. And this happens very fast. Right? So fast that from a user point of view, all of this seems to be running parallel at the same time. Okay? Now, once you suspend a task, right, and run another one, and at a later time, you need to come back and then resume that particular task. Right? Now, think about what does the operating system needs to remember in order to resume a task. Okay. Right. So maybe task 1 was executed, and then you switch to task 2 and 3, and then now you switch back to task 1 again. Now, in order to seamlessly and smoothly switch back to task 1, the operating system has to remember something about the previous execution of task 1. What are some things that the operating system has to remember? Any idea? Okay. Any ideas? Okay, think about, let me give you an analogy, right? Let's say you are happily studying in a discussion room in Comp 1, right? And then somebody come in, knock on the door, say, sorry, we need this room for a meeting. And then you got chased out, you have to go to another place and then continue your reading. Now, this means that you are reading halfway, you get suspended, right? And then later on at another place, another time, you have to resume, continue your reading. So what do you need to remember, right, in order to continue reading? Program counter, very good, right? So you have to remember at least the point where your execution has stopped previously. Okay? So you don't want to stop, and then when you resume, you start executing from the beginning again, right? That doesn't make any sense. Just like when you continue reading, you don't start reading from the first page. You have to remember at which point in time you have stopped reading. Okay? So first thing is that you have to remember your program counter value. Right? So that when you resume, right, you can continue from the previous program counter. What else? Registers, yes. So program counter is also part of a registers, right? So let me generalize this answer to just registers content. Right? So when you suspend, you have to take all your content in the registers in the CPU, save it somewhere, so that when you resume later, you will restore the same value. Right? Because the CPU has only one set of registers, but he cannot keep so many for all the tasks they're running. So he has only one copy. So whenever you suspend the task, you have to take all the values in the register, keep it one side, and then when you resume later, you put it back. Okay? Registers. Very good. What else? Think about what other things does a task needs. So registers are for CPU. Right? What other things that you might want to store and files that are currently open? Very good. Right? So, for example, a task might be reading and writing to a file. Right? It might be reading through a file halfway. Right? And then it gets suspended. And when he go back, he has to remember which file he has been reading and at which point of the file he has been reading. Same thing with writing. Right? If you write halfway, you get suspended, you go back, you have to remember which point is that, which point in the files have been written and so on. Right? So you have to remember about the files. Right? I call it the file descriptions, right, or file pointers. So these are information that can identify what are the files that has been opened and read and written to by a particular task. What else? Sorry? Memory, yes. So the task is also accessing data from the memory, right? And remember from last week, what is stored inside memory? So you have the code and you have the data, right? The variables, everything that the program is running on. Now, the answer memory here is actually a bit tricky. Okay. Now there are several things about this. So first of all, memory is actually shared. Right? So if you have, let's say, 2 GB of RAM on your computer, and you have enough, if you have enough RAM for all the tasks, then they happily share the memory. Right? When you suspend the task, the data that is used by this task can stay in the memory. Okay? So in this case, then there's no need to remember the content of the memory. However, if you don't have enough memory for all the tasks, right? When you switch to another task, you have to free up the memory for the next task. So when that happens, you have to take all your content in the memory, again, save it somewhere, and then let the next task have full use of the memory. And then when it is your turn to resume, then you kick the content of the other task out of the memory, and then you load your stuff back into the memory. Okay. Right? So there is a conditions to whether you need to remember the content of the memory or not. Right? In simple systems where you have enough memory for all the tasks, you don't have to. But in all modern computers where you have lots of tasks running and you need lots of memory, normally this is something that happens. And when we talk about memory in, I don't know, lecture 7, around lecture 7 or 8, we are going to see how this is actually done in details. Okay, so we have memory. What else? Now, in the pre-class activities, I ask you to just open up the task manager on Windows or activity monitoring on Mac, just to see what are the tasks, what are the processes running on your computer. Now, if you've done that, you will have seen that there are additional information that is associated with a process, okay, or with a task. So this includes things like how much CPU time this task has used, or how long has this task been running. Right? Now this information is what we call accounting information. Right? So this is basically information that is associated with individual tasks, to say how long it has been running, how much memory it's using, and so on and so on. Right? This is just for bookkeeping. Now, when you suspend a task, you have to remember all of this information, so that when you resume, you can continue doing your bookkeeping. Right? You don't want to reset everything back to 0 every time you resume a task. Right? Okay. So these are some information that you need to remember. There are other things like, for example, the state of the network socket as well. And if you haven't taken 2105, if you have taken 2105, then you'll know what this means. If not, then don't worry about this. Right? Basically, this just means that what is the state of the connection that this process has with another process, and so on and so on. Okay. So these are some things that you need to remember when you switch, when you suspend a task and when you want to resume it later. Any questions? Okay. So now, with that understanding, I can now explain to you what is a process. Now, a process is basically an abstract object or abstract structure that keeps track of the code of a running task or a running program. It's data, right? Things that is stored in the memory, things that accounting information, for example, and the context of execution. The context of execution here means the state of the execution of the process. So, for example, the program counter, right? Execute halfway, you have to suspend, resume. This is the context of the execution. Right? So, a process basically consists of these 3 items. Okay. So now let me quickly show you a short demo. Let me try to put this back onto my ear. Okay, so if you have tried the pre-class activity, you have seen something like this. If you tried it on Linux or even on Windows. So what I'm going to do is I'm going to show you a process, a command called PS on my computer. And PS basically just lists down what are the process running. Now in this case, it is just showing 2 processes, right? Because this is what has been this is what have been running since I logged in. Now, if I do a PS minus EAF, for example, it's going to show me all the processes that is running on my laptop currently. Right? So these are all the processes. Let me just do this so that it can be formatted nicely. So as you can see, there are lots and lots of processes running on my laptop at the moment. Okay? Not all of them are actively being executed by CPU, but no, they are also, most of them are waiting to be executed. There will be one of them that is currently being executed as I run this command. Okay. Now, just to make things clearer, I'm going to show you the information on a graphical user interface. So I'm going to launch the activity monitor. So this here you can see all the processes that's being run. Right. This is a process name. This is me. I'm running this, and this is the amount of CPU time being used by this process. So you can see that the process that is taking up the most CPU time is the my video recorder, right? The one that is currently recording the screencast. And here you can see the different accounting information that's being associated with the process. Okay. Now this is a very useful thing to study and understand. Right? And we are going to revisit activity monitors and PS command many times over the course of the semester. Okay. So this is a process. So as you can see, process is a very fundamental concept in operating system. It basically provides an abstractions for a running task on the computer. Okay. Now it is not true that you have one process for every application or every program. Okay. You can have one program or one application that runs multiple processes. So for example, as you can see here, I have 3 different processes that corresponds to the same program. Okay, and as also you will see next week. So when you run a browser, certain browsers launch many different processes just for browsing the web. Okay? So processes is not the same as program, right? But it basically abstract out whenever you run something, your code, you have the data, you have the state of execution, right? That itself is one process. Okay, so this is the abstraction for the process. And now let's move on to the next abstraction. Right? It's called the address space. Now, just now I said that for every process you have some you make use of certain data or certain region in the memory to store your code and store your data. Right? Now, in order for security reason, right, we want to prevent one process from accessing the memory content that belongs to another process. Right? So for example, if let's say you log on to SOC server and you see that your professor is editing a file called exam, and you want to see what he is editing. You cannot, right? Even though you would like to, because these are 2 different processes. Whatever process that you launch is going to be protected from the process of your professor. You cannot see each other's memory content. Right? Not only of course, you cannot see each other's memory content, you cannot also modify the content of another process. Okay? So we need to be able to separate the memory content of one process from another process. Okay. Now, what is the best way to do this? Now, let's look at one very naive method. Okay. Now, whenever a process try to access a memory location, right, the operating system will do a check. Say, okay, this memory location is used by who? It's used by the other process. Okay, sorry, it cannot access. So this is one way where you can protect the memory of one process from other processes. But if you're going to do this checking, it's going to be very troublesome and computational intensive, because the operating system have to keep track of exactly which region in the memory is used by which process, right? And these are not fixed. As the program runs, it needs more memory, it needs less memory, these regions can grow and shrink. So the operating system would have to keep track of all of that in order to use the methods that I just described. So the designer of operating system come up with this idea of an address space. Okay? So the idea of address space is as follows. You don't tell the process what is the actual memory addresses that is being used by a process. Okay? In other words, a process doesn't know what is the physical location of each of its data and code. Okay? What the operating system provides to a process is a logical address instead. Right? So you provide a logical memory address to all the processes. And the logical memory address would start from, let's say, 0 up to the size of the size of the memory that is allocated to a process. Okay. So for example, in a process case, I want to access memory location 0. Now this 0 is the logical address. It will be translated into a certain physical address in the memory. Okay. So now, there is no way for one process to read or write the content of another process, because all he has access to are logical memory address, right, 0 to some maximum number, and he can only access to locations over here. Another process, let's say this is process P1, another process P2, he can also access logical memory from 0 to the maximum value. But these two are mapped into different regions in the physical memory. Okay. So there is no way for this process to be able to access this region here, because they have been separated and everyone is given its own address space. Okay. So this is the second abstraction that is provided by the operating system. Okay. So the first one, the process is for sharing of CPU, and address space is for sharing of memory. Okay. So with this, every process has its own address space. And even though a process may occupy different physical memory regions at different times. Now, having this idea of address space is also important for the following reason. Okay? Now, imagine that your process it might occupy different regions of memory at different times, right? Why does this happen? Remember, in the earlier example, I said when the task gets suspended, its memory might be, he might have to move his stuff out of the memory so that another task can run, right? So once this task finished running, he has to move his stuff back into the memory. But when he moves his stuff back into the memory, it might be located at a different location. Right? Might be at a different location. So a process might occupy different regions at different times. Right? It might move to the top, to the bottom. It might be split into two, one at the top, one at the bottom, and so on and so on. But when this happens, the executable code of the process must remain the same. Okay. Now, take for example, suppose you have an instruction that tries to load a content from a particular memory address into a register. Right? Let's say my instruction says load from address X to register Y. Okay. When you generate this binary code, right, what should you put in the location for in place of the address X here? If you put the actual physical address as is being shifted around in the physical memory, your instructions might not be correct anymore. Right? You might say, I want to load data from this particular address, let's say A87E7C, for example. You might want to load from this address. But as the code shift around, this might not be what you actually want to load. It might not even be the data that belongs to you, it might belong to another process. So we cannot put physical address here. If we use address space and logical memory address, this solves our problem. Okay? Because logical address is allocated for this process, and the process will know exactly which logical address it wants to load from. When it shifts in the physical memory, the logical address remains the same. Right? So if we use logical memory address, then we can prevent the problem. Right? We don't have to worry about the program being shifted around in the physical memory. Okay? And the executable code can remain the same. So the only question that remains is how do you map from a logical memory address to the physical memory address? Okay. So let's say that this is my physical memory, right? And you have a process running. This process has again the code, the data segment, stack segment, everything in the memory being allocated to this process. And let's say that the CPU executes an instruction, let's say load from address X into register, let's say RY. Okay. Now this X, let's say that it has a certain value. Okay. For simplicity, I'm going to say, let's say you want to load from address 1000. Right. The operating system will then translate this 1000, which is a logical memory address, remember, to the physical memory address. Okay. Now, in common architecture, this is usually done by a hardware called MMU, okay? Memory Mapping Unit. Now, when the CPU try to execute the instructions, he put a request to fetch data from the memory. It passes in the logical address. The MMU will translate this to a physical address. Let's say the physical address is something like this, and then you can get the data from the physical memory and then send it back to the CPU. Okay. So there is usually a hardware unit that do the translation between the logical and physical address. There are other methods which we will cover in more details in maybe lecture 7 or 8 of the course. Okay. So this is the abstractions for sharing of memory, the address space. The next abstractions is actually fairly well known to you. Right? It's called file and directories. Right? So files basically is an abstraction for sharing the storage device. Right? You have different users trying to put data on different locations on the disk, and in order to prevent you from worrying about where did you store the data on the disk, the operating system hide all of this from you, and it provides the notion of a file. Okay? It also has a notion of things like disk quota. Right? Disk quota means that every user has a limited number of space on the disk. You cannot use more than, for example, on some file I think it's 2 or 3 gigabytes, I don't remember. Right? There's a certain limit to the number of files you can store on the Unix servers. Right? So you have a notion of quota, you have a notion of, let's say, file permission. Right? You can, if you have data on the disk, unlike memory where you cannot allow other people to look at, modify the content of memory, sometimes you want to share your data on the disk with others. Right? So you can change your permissions on the disk so that others can read or write to your files. Okay? Okay. So I won't go into much more details on this because I think all of you have been using computers and you should be familiar with the abstractions of files and directories. Okay. There are 2 things, however, that I want to highlight to you, and this is particularly true for the Unix operating system. Okay. Now, the file abstractions on Unix is not only used to represent data on the disk. They can be used to represent devices. They are used to represent special things on the computer. Okay. So there are 2 types of files. These are usually called the special files, right? And they can be either a block special file or a character special file. A block special file means that you read and write through the file, one block at a time. And then character special file just means that you read and write 1 character at a time. Okay. So here is one example of a special file on a Unix system. So on Unix, if you go to /device /mice, for example, this is a file that corresponds to your mouse. Okay? Now, mouse is not a file, right? It's not something that you store on the disk. But from the Unix point of view, it is something that you can read data from, and that itself is abstracted out as a file. So you can actually open up this device and you can read your mouse position from this file. Okay. Of course, for special files, there are certain restrictions. For example, it doesn't make sense for you to write the position that you want your mouse to move to into this. There are other devices, for example, normally you have something like device sound. So this will represent your speaker on your computer, and you can write whatever sound you want your speaker to play into this file. Right? So you can open the file, you can write it as per normal, and you can hear sound being played on your system. Okay. So these are examples of special files on Unix. Okay. And we are going to look at these in more details when we talk about files later in the semester. Another thing that we were going to look into details, including in one of the labs, is something called a pipe. Now, a pipe is a special file that allows you to read and write to another process. Right? You can read and write to another process. So you can open up a pipe, you can set up a pipe to another process, and you will write to it just as you're writing to a file. So let's say I have a process P1, I have another process P2. Okay? I can set up a pipe between them. Okay? And P1 can write to this pipe just like he is writing to any file. Right? And as he is writing to any file, these other process can read from the pipe as if it is reading from a normal file. Right? So as this guy is writing, this guy is reading, the process P2 will read whatever process P1 is writing. So a pipe basically is a conduit or a channel for communication between two processes. Okay. Now let me show you an example of pipe. Okay. Now just now I showed you the command called PS. Right? So this will list all the processes running on my system. Okay. Let me now show you another command called WC. Okay. WC is a program for counting the number of words, the number of lines, and the number of characters. Okay. So, for example, I can say WC. Let me just count the number of lines. So I put -L, and then let me just type in some random thing. Right. So there are 3 lines. So WC will return me 3. Basically, it just count how many lines is there in the input. Okay. So how do I use a pipe to count the number of processors on my system? Okay. So I can take the output from my first command, which lists all the processors running, and instead of letting it write to my screen, I will ask this command PS to write to WC. Okay? So I will use this character, it's called a pipe character. So I will pipe this command to WC -L. Okay? So now I have set up a pipe. So over here I have my PS, and then I set up a pipe to WC. Okay. So let's see the output of this command. Right. So it says 74. So this means that I have 74 processors currently on my laptop. Okay. So this is an example of a pipe. You will get to play with it in your first lab, and you will get to implement it at the end of the semester. Okay? Any questions so far? Okay. So let me get back to the slides. The final concept that I want to talk about before I take a break is shell. Okay, so what is a shell? A shell is basically one of the 2 user interfaces provided by the operating system to the user. Now, I mean this is to user as in to human user, not to other programs. Okay. The first one that I think most of you are familiar with is a windowing system. Okay. So you have Windows, you can open window, close window, maximize, I think you know all of that stuff. A shell is something that I believe most of you are less familiar with. Some of you might have know how to use this, but most of you are more comfortable with using a windowing system. what I have shown you in the demo just now, this is basically a shell. I am actually interacting with my operating system through a shell. To be more precise, I am currently using a shell that is named bash. Right? So this is the name of the shell I'm using, and I'm actually typing command, telling my operating system to say, hey, now launch this command for me, and the operating OS will launch this command, it will launch this command. Basically, it will create two processes, and it will create a pipe between these two processes. Okay? So I'm actually telling my operating system to do stuff. Okay? So this is the interface to the operating system. So you will make use of the shell quite a bit, and also towards the end of the semester, you'll write a shell of your own. Alright, so this is a good time to take a break. So I have covered the different, abstractions for the OS. And I'll take a break now, and I will resume the class at, let's say, 1 p.m. Okay? So I'll talk to you later. Hi. Yeah, you can just try anyone. Just let the PA know. It means that who you are, you're not registered to the class, but you want to
But they will not take comments.
we'll note down who is there. So, just in case we want to clarify something after the class as well, we know who attended. Yeah.
So it's possible that there are two different classes.
Yeah, yes, it's possible. Yeah.
So there's a formal system for registration.
Yes. Are you formally registered for the class, or are you just for the
No, I'm taking the class.
You're taking the class, okay. Yes, there's a formal system. I think you have to go to course or something. If the bidding has already ended, then you can just email the person at the end of the class. So that
So they are tutorial, those tutorial first labs. They will still class lab.
yeah, no, those two basically just handle registration.
Oh, I see.
Just registration. You got down your name? You want me to write down your name?
Slides.
Slides. Yeah. But I didn't put it on the slide.
Oh.
I didn't put the other stuff. Maybe I can write it down for you.
Just email them which tutorials.
Then CC, just CC.
Where can I find the list of tutorials?
It's online.
It's online.
It's online. If you go to IVLE, yeah, go to timetable.
Okay.
I can. Yeah. Okay. You have appeal to course, right? Okay. So if you haven't received anything by next Monday, you can just come to the lab just for 1 week until you finalize. And just let the PA know. From the other class.
to hack?
Hack the I think I'm not sure what they're going to do in phase 2 to 3. There's a call of phase 2 to 3 called synchronization. That one will go much deeper and connect code. I'm not sure whether they are really doing it or not. Another possibility is the cost of security. They might go into it's really hardcore. So yeah. All right. So break is over. Okay, let's get back to our class. Okay. Now, last week we talked about user mode and kernel mode, right? And I show you this picture, which shows that you have operating systems that provide different interfaces to the applications. And the interfaces that are provided by the operating systems to the applications are known as system calls. Okay? And I briefly talked about how system call is executed, but I didn't go into much details. So with what I talked about today, with your understanding of processes especially, I think I'm now ready to explain a little bit more about how system calls really work. So this is also a picture that I showed you last week. Now you have a program running, and then this program wants to invoke services by the operating system, so it makes a system call, and the program counter will jump to running a code or instructions provided by the kernel. Okay. Jump and start to run code provided by the kernel. And I also say that there's a bit in the program status word that's being switched to indicate that you are now in the kernel mode. And remember, in the kernel mode, you have no restrictions. The code you can execute any instructions, whereas in user mode, there's a certain restrictions to what you can run and what you cannot. Okay. Now, to invoke a system call, it involves the following two things. Right? So, first of all, there is a common set of routines to set up and clean up the system call. Now, this is common to everybody, or common to every system call, regardless of what you want the system call to do. Right? You might make a system call to say, read a file. You might make a system call to say, create a process. They might actually do different things, but the setup and cleanup routine are the same. Right? So there is a common setup and cleanup routine that is common to all the system calls. And then there is another set of code that actually do the work of the system call. Okay. Now, last week I threw up this term, right? System call handler, without really explaining what this is, right? So system call handler basically refers to this thing. Right? Is to handle the invocation of a system call, and of course to clean up afterwards. Now there's another part of the code that actually do the work of the system call. When you call the system call to read, it actually reads. When you do create a process, you actually go and create a process. So this is doing the actual work. So this is called the system call service routine. Right? Provide the actual service to the system call. I'm missing a picture here, which is not good. Where is that picture? Just hold on a second. Let me. Here it is. Is this on your slide? Is it no? Okay. Sorry about that. So I guess you will have to write this down. Okay. So this is an important slide because it explains to you what actually happens in the when you call the system call. Okay. So let's say you have a code running, you have an application code running, and then somewhere you make a system call. Now, those of you who read the book and read the discussions on the blog, there has been some discussions about the difference between system call and the actual system call and the library call. Right? Normally, the user program don't call the system call directly. Normally there is a library function that wraps around the actual system call. Okay? So when you call, let's say, a function read, you don't actually call the kernel system call directly. You actually call a library function. So this is a function written by the library provider, let's say C library provider or Java library provider, that hides the actual calling of the system call from you. Okay? So you normally call what we call a library wrapper. Okay? So your code execute, and then call read. So it will now call another function called read, and then it will execute, and then it will call the actual system call. Now, when you call the actual system call, it causes the process to stop running, and now the CPU will not execute the code in the kernel. Okay? So this is the point in the picture where your arrow was pointing to the user code. Now it jumps to the code that belongs to the kernel. Okay? Now this is the setup routine, right? So you do all your setup here, and the things that you do in the call setup include, for example, switching to the kernel mode. Right? You change the bit in the CPU register to indicate that you are now in the kernel mode. Now, because you are now suspending the running process to execute the code in the kernel, you have to remember the context of execution of the process. Right? Remember, just before the break, we talked about what are the things that you need to remember before you suspend so that you can resume the process later. Right? So all of that you need to remember, you have to keep it on one side. And then this step also involves passing the arguments of the system call from the user process to the kernel. So maybe in this system call, I have some argument. Let's say if I want to read something, I must say how many bytes to read. After you read, where do you want to store, and so on. All this information has to be passed to the kernel. Okay. So you also pass the information to the kernel. And then finally, you determine which actual service routine, or say service function here, but it's the same thing. A service routine that you need to call. Okay, so in this case, it do a setup and then say, okay, now I want to call this service routine. So your code execution, your execution comes to here. This is the one that actually do the work. It actually read something and then return here and execute, and then now you clean up. Okay? So the sys exit here refers to the cleanup phase, and to clean up, there are a few things that you do. You can indicate whether there's any error. Right? Check if there is error. You can also check if you should continue the execution of the previous process. Now, why don't you just straight away return to the previous process? Now, the previous process has already been suspended, right? So, at this time, the CPU has a chance to make a decision to say, for example, is there any other process that is more important that now that I can execute now? Right? So this is a opportunity for the kernel to switch to run another process. Because you're already suspended, there's no point going back to the same process again unless necessary. And if this process needs to be restored or other process needs to be restored, system exit will restore the process parameter, the context of execution, and then you return to the user mode, meaning it goes back and then switch back the bit in the CPU register, right, to indicate it's back to the user mode. So you come back to here, finish execution, and then come back to the user code, and then exit. Okay. Now the slides that I have list down the type of things that you do when you do system call setup. Right, these are the 4 things that are listed, and also what you do when you clean up. And this is what I actually mentioned just now. So all is well, except that I haven't explained to you how we actually go from the here in user mode, running the user process, to here where I'm running the code in the kernel. Okay. Now, if you think about it, you cannot actually do this just like a normal function call. So in a normal function call, what you do is that you are calling from code that belongs to the same process. Now you are calling or executing code that belongs to the kernel. Right? So it's not like the normal function call. So you need to do something special in order to trigger the switch from the user code to execute this system call handler. And in modern operating system, this is typically implemented using a software interrupt instruction. Okay. The textbook use the instruction called trap. They call it the trap instruction. In x86, the Intel architecture, the instruction is actually called INT, which is a short for interrupt. Okay. So whenever a process executes this instruction, it causes the CPU to jump to a particular piece of code in the kernel. Okay. And so the system call here, the actual sys call here, this is triggered by the interrupt instruction. Okay. So this is how system calls actually works in details. Okay. Is this on your slides? Yes. Okay, good. So now let me briefly talk about the different ways you can structure your operating systems. Now, if you look at the textbook actually has a few more details. They have a few more different ways of structuring OS. But I'm going to just talk about 2 which I think is the most extreme and also most commonly used ways of structuring the operating system. Okay, so the first one that I'm going to talk about is what is called a monolithic structure, and it's being used in the Linux kernel. So remember in the earlier program, earlier picture, we have different applications over here, right? The user programs, and then you have the system call interface that allows you to access to the kernel, right? So this thing will be the kernel over here. Okay. So when you make a system call, you can switch from the user mode to the kernel mode. Okay. So this is triggered by the user program. There is another way where you can go from user mode to kernel mode. And that is if you have something that is initiated from below by the hardware. Okay. Now, if you've taken 2100, you're familiar with different hardwares, how interrupt works and so on. Right? So a hardware, let's say a mouse want to send some input to your systems, you send an interrupt, and then this interrupt, so hardware signals will go to the CPU, CPU will be interrupted, you will then execute whatever code that is responsible for dispatching, for handling that interrupt. Right? And all of this code is part of the kernel as well. Okay. So you can enter from user mode to kernel mode in two ways. One is through system call, right, or software interrupt, or the other is through hardware interrupt from the bottom. Okay, so these are actually the two interfaces provided by the kernel. Now within the kernel, we have mainly three things. We have process management to manage all the different processes. We have memory management to manage the logical memory, physical memory, allocation of memory, etc., etc. And then we have the I/O component that manages all the I/O devices, like your pen, your display, your printer, everything. Okay. Now the I/O component, we can further divide it into different components. The device drivers is an important part that handles all the different I/O devices. Right? So the device drivers are device-specific code that tells the operating system how to manage a particular device. Okay. So, for example, if you buy a new piece of hardware, let's say you want to buy a tablet, right, for your PC. Your PC might not know how to talk to this tablet. So you need to install a device driver, and this device driver will talk to the OS and talk to the tablet. Okay. So at the bottom here we have drivers that communicate with the hardware. And we also have the file system or virtual file systems. That, as I mentioned to you, you have slash devices, something, that provide a file interfaces to communicate with these I/O devices. Okay. So this is how the Linux kernel is structured, and it is called a monolithic kernel. It's called as a monolithic kernel because everything that I mentioned is put into one single piece of kernel code. Okay? As opposed to the next design, okay, which we will see. Now, monolithic kernel, if you use monolithic kernel, it's very easy for your kernel to get bigger and bigger and bigger. And the reason is that there are more and more devices that need to be supported. So, for example, in my old version of Mac OS, it comes pre-installed with 3 GB of printer drivers. Right? They remove it in the Snow Leopard, but in the old days, you have tons of drivers that come pre-installed, so that you can plug in any printer and it will just work. You don't have to install any drivers. Right? But this just means that if you put all of that into the kernel, then this means that your kernel is going to be huge. Right? So most modern operating system doesn't do that. Right? What they do is they have something called a dynamically loadable kernel module. Right? Dynamically loadable kernel module. And the purpose is to keep the kernel small, but still extensible. Whenever you want a new driver, you take that driver and then you load it into your kernel. Okay? There's C programming tricks that you can do in order to load something dynamically. Yeah, this is also something being used by Microsoft Windows and Mac OS as well. So this keeps the kernel small, but it can still keep it feature-rich. Whatever features that you want to know, add new devices and so on, you can load them as dynamically loadable module. But this doesn't mean that the design is not monolithic. The design is still monolithic because everything that you load still runs in the kernel. Okay? Now let's look at the alternative design. This is called the microkernel. The microkernel is very similar, as you can see here, except that the I/O components have been removed from the kernel, and now it is part of the user space. Okay. So all the device drivers, the file systems, all of this is running in the user space. In the kernel, you only do memory management and process management. Now, this type of architecture is being used in operating systems, especially for small devices, because you really want to keep the kernel small. So, for example, two favorite examples is Q1X, right, so embedded OS. The Symbian OS also. Symbian OS is the OS that is running on Nokia phones. Right? Now, what is the pros and cons of this architecture versus this architecture? Now, for monolithic kernel, the disadvantage is that you have to load device drivers that is written by a third party into your kernel. Okay. Now remember, everything that runs in the kernel runs in kernel mode. And in kernel mode means that there is no restrictions. You can do anything. Okay? So security is one problem. Right? If you download a driver that is written by a malicious person, that driver can do funny things to your computer. Even though it is not malicious, if the driver is buggy, it can still crash your computer. Right? Because it has access to everything in the kernel mode. Okay? So which is why I think starting from Windows XP and later on, the drivers has to become, the drivers that you install, so there's something called certification of the driver or something like that, which means that you have to get Microsoft seal approval says your driver is okay to be running. Okay. And sometimes when you run your program, run your Windows and the Windows crash with a blue screen of death, it's not always Microsoft fault. It could be the fault of a third-party driver that is running in the kernel mode. Okay? So this is the main disadvantage of the monolithic design, besides having a bloated kernel. So how about microkernel? So microkernel move all of these things onto the user space. So whatever device drivers that you install is going to run in user space. So the problem here is that since all of these are now running in user space, in order to access the services by the kernel, you have to make system calls. You have to make system calls. And the more things you put outside the kernel mode, the more system calls you have to make, because you have to cross this boundary even more often. Okay. So in fact, this becomes a bottleneck in the Windows operating system. So I don't know how many of you remember, old enough to remember this, but there was a version of Windows called Windows NT. So this comes after Windows 95, supposed to be completely new kernel architecture. and so on. But later it turned out that Windows NT is even slower than Windows 95. And the reason is that because of this microkernel architecture, there's a lot of system calls that needs to be made. And so later on, the Microsoft started to move some of these things back into the kernel to optimize the performance. Okay. So these are the two structure of operating system that I want to talk about. The microkernel architecture that keeps I/O components in the user mode, and the monolithic architecture that keeps everything in the kernel. Okay. And there are pros and cons of different architecture. Okay, so that concludes the OS materials that I want to talk about today. Right. For the rest, I don't have much time left. Okay, for the next 15 to 20 minutes, I'm going to give a brief introduction to C programming language. Okay. And as I said, if you know C very well, you look through the slides, you understand everything, you are free to take your leave. Okay. So let me start by highlighting the difference between C and Java. Right? So Java is an object-oriented programming language. When you write Java code, you organize your code into a set of classes, and your classes have methods and members. When you write a program in C, right, C consists of a set of functions and structures. There's no concept of class, no concept of objects. Everything is just functions, and you have your code is organized into functions, and your data is organized into structures. Okay, so this is the first main difference. The second difference is that there are certain data type you are familiar with in Java that's not available in C. For example, there's no byte data type, there's no boolean, and there's no string class. And for each of these, you can use character, integer, and array of character respectively. In Java, in order to create an object, you have a new operator, right? You have A equals to new A, something like this, to create a new object. In C, there's no such thing. Now, in order to manage an object, you have to explicitly declare a pointer, which I will talk about later, and you must explicitly allocate and deallocate memory. Right? You call malloc to allocate memory, stands for memory allocation, and you call free to deallocate memory. Now in Java, all variables are reference type. Right? Remember in Java, you have primitive type and you have reference type. Except for boolean and numeric type like integer, character, long, byte, and so on, everything else is a reference. String is a reference, for example. In C, everything is a primitive type. Right? In other words, it holds exactly the value of that exact type. There is no, you don't declare something that then it becomes a reference. If you want something to be a reference, you have to explicitly say this is a reference. Okay? So C is more explicit than Java. In Java, sometimes you want to use external utilities, right? In which case you have to import them. You say import.java.util.star, something like that. Right? In C, you don't import things, right? But if you want to use any external functions or external type, they must be declared. In other words, you have to say, okay, this is a type called X, Y, Z that defined somewhere else, and I want to use it in my code. But this is normally made easy by using the hex include statement. Okay, I will talk about hex include statements later. Okay, so these are the main differences between Java and C, and there are many other differences that you can read online through the resources that are posted onto the blog. Okay, now let's look at some real C programs. Let's start with this one. This is the simplest program that you can write This is a function. You have a main function, just like in Java. Right? Your code starts executing from the main function. And the main function always returns an integer. And in this code, I just have one statement which returns 0. So you can see the syntax of C is very similar to Java. You have a semicolon, you have a curly bracket, and so on. Okay? So it's very similar. Let's look at a slightly more complicated program. This one prints the hello world. Okay? Now, I call a library function called printf that prints a string called hello world. Now, this printf is an external function. It's not something that I wrote, it's something that somebody else wrote. And I have to find out what is the header file that includes this function. So how do you find out? Well, you go to your shell and you type man whatever function that you want to call. Okay, sorry. Let me see here. Okay, so this is a printf function, and for printf functions you have to include this file called stdio. It stands for standard IO library. Okay. So whenever you need to call a function, you're not sure what it does, you just check the man page by typing man followed by the command. Okay. Now this is a slightly more sophisticated program. Now I add in integer argument C and argument V as a parameter, and this is the same as your public standard white main, the arguments that you pass into your Java program. Right? It's just that in C you write it this way. Here I call a function called say hello, and say hello is defined here, and passing times will then print out hello world for these many times. Okay. Here I call a function called a to I. This is to convert. Okay, let's see what a to I means. So I do man a to I. Right. So this is to convert an ASCII string to an integer, and in order to call these functions, I have to include this library. Okay. Okay. So now let's look at something that is can be fairly confusing if you come from the Java world. Right? If you program in Java, you don't have to worry about pointers or references, because everything is hidden from you. Now in C, you have to worry about the addresses or the pointers of variables most of the time. So let me now explain to you what is pointers. Now let's go back to the basic. Every variable in C has a certain location or occupy a certain location in the memory. Right? So if let's say this is a memory, right? You have a variable, so this variable will occupy a place in the memory. Now if he's somewhere in the memory, he must have a memory address. Right? It's a logical memory address. And it can store a value. Okay? So for example, integer x, right? So x can be in certain location in the memory, and it can store certain value. Now, just to make things easier, I'm going to use a metaphor to explain this. So the metaphor I'm going to use is that a variable is basically a box, right? So the box, you can put a value inside. Right? You can write the value on a piece of paper you put inside the box. But a box also have an address. So basically this is a label that identifies the box. Okay? So if you have an integer x here, you have a box with the value and the address. Now let's look at the basic of the assignment operator. So let's say that I have a following code. Let's say x assigned to value of 2. So what does this assignment operator mean? So there are two sides to this assignment operator. You have the left-hand side and the right-hand side. Right? So the assignment operator means that I take the value on the right, store it into the address on the left. So I interpret the left and right-hand side differently. The right-hand side is interpreted as the value. The left-hand side is interpreted as the address. Right? So I take the value on the right, put it into the location on the left. So this is the assignment operator. Okay. So you have any questions about this basic? What is a variable? What is assignment operator? Make sure you understand this. Okay. Okay. So let's walk through this example very quickly. I have two variables, right? So I have two boxes. One corresponds to x, one corresponds to y. Now these two will have some address, let's say 1000 and 2000. And when I say x equals to 1, I take the value on the right, which is 1, I put it into x. What I mean by put in x? I interpret the left-hand side as the address. Right? So I put it into the location of x. So I put 1 over here. Y equals to 2. I put 2 over here. And when I say I assign x equals to y, I look at the value of y, right, which is 2, and x I interpret it as the address of x. So I take 2, I put it into x. So the content of x becomes 2. Okay? So everybody should understand this. Right? It's a basic variable assignment. Okay. So now things get complicated. Now, instead of declaring a variable called integer x, I declare a variable called integer star x. Okay. So integer star x means the following. We say x is an address. Right? X is an address of an integer. Now x is still a variable. Right? A variable means that you still have a box of x. Right? You still have a box for y. But now what you put inside x, instead of you put an integer, you put an address. So this means if you want to put something into x, you have a piece of paper, you write down the address, and then you put that address into the box of x. Right? Same concept as before, except that now what you store inside the x is now an address instead of a number. Okay, so let's see the rest of the code. So y equals to 2. Okay, so let's say I have the address of the boxes as 1000 and 2000. So let's say y equals to 2, you put 2 inside y. Okay, now I say x equals to %y. What does %y mean? %y means that this is the address of y. Okay? So in the third line of code, remember, this is an assignment. So we interpret the right-hand side as the value. Okay? So this means I take the value of the address of y. What is the value of the address of y? 2000, right? Because y, the box y has address 2000. And I interpret the right-hand side as the address. So I put 2000 into the box of x. Okay, follow so far? Okay. Okay. So this one just means the address. So I put address of y into x. Okay, let's look at the third statement. Star x equals to 3. Now what is star x? Now remember, on the left hand side I must interpret this as a location. Right? The location where you want to store the value. Now the operation star here means that you take the address and then you follow that address. Okay, now x is an address, right? So you take the address, you just follow the address, you see where it is you put. Okay. Now, so what happens here? So you start x, so you look up the box x, you take out a piece of paper inside, oh, it's an address 2000. So you go and look for the box 2000, and then you put the value 3 inside. Okay. So when I say star x equals to 3, I will look at 2000, I look for box 2000, I found it, I put 3 inside the box. Okay. Now there's another way to interpret this. You have x, you have y. Right? Now instead of putting an address of y here, I can put a piece of string and then I tie this piece of string with an arrow pointing to y. So when I do star x, what I do is I just follow the pointer, follow the string. Right, so I take the box x, I say, oh, there's a string, piece of string tied to it. Since there is a star operator, I'm going to follow the string. So I follow the string, this string will lead me to the box y, and then I put my value 3 inside the box. Okay. Now because of this, x is also called a pointer. Right? So a pointer basically is a term for addresses of variables, and it's called a pointer because you can think of this as it is actually pointing to another location rather than it is a value. So I say star x equals to 3. So this becomes 3. Right? And this star operator is called a dereferencing operator. Basically, if you see a star, it means you have to do one extra step. You cannot just use the box, you have to follow the address in the box to go to another box. And you can do this multiple times. Right? I can have star star x. If you see something like star star x, means you have to follow the pointers 2 times, or you have to look up the address 2 times. And you can add more stars if you want to. Okay, now let's look at the last statement. The last statement says y equals to star x. Okay, y equals to star x. So now the star x doesn't appear on the left hand side, it appears on the right hand side. It appears on the right hand side. Now, if it appears on the right hand side, then you interpret that as the value. So what is the value of star x? Again, you look, it's x, so you look up the box x, and then there is a star, so you follow the pointer. Now this pointer brings you to y, right? Brings you to y, and then you interpret the value, so you look at the content of y, which is 3. And then you put this back into y. So you take up 3, you put it back. Okay. Now if this statement is instead, let's say, star x plus 1, sorry. If it is star x plus 1, then what you will do is that you take out this value 3, you plus 1 becomes 4, and then you put it back to the location of y, which is here, becomes 4. Okay, so the star x can appear on the left-hand side or the right-hand side. If it's appear on the right-hand side, you will interpret that as a value. Left-hand side, you interpret that as a location, just like normal. Okay, now you go back and think about what is star y and ampersand x, and we'll talk about this in the next lecture. Okay, now using pointers is tricky. It is the cause of many bugs, especially in C programs. Okay? Because this is tricky, I want to at least cover this part first before I let you go for today. Okay? I won't have time to cover the rest of the slides, which I will do next week. Okay, so let's look at this code over here. So again, I have integer star x. So I have two blocks. I have x and I have y, right? And they have addresses. Let's say x is 1000, y is 2000. Okay. I say integer y equals to 2. I put 2 into my box of y. And then I say star x equals to 1. So what will happen? Okay. Star x equals to 1. So this means that you look up the box x, right? You look at the content, and then you follow the content. But what is wrong here? Yes, what is wrong? It's not initialized, very good. So this box hasn't been initialized for anything. So now, whatever value here, you will follow, and then you will change that box, the content of that box to 1. Okay? So now you see why using pointers is tricky. Because you are accidentally changing another memory location just because you forgot to initialize what is this value. Okay? Now, if you are lucky, this is some invalid value. Let's say if the value is 0, which let's say refers to a memory location which you cannot modify. And so when you say star x equals to 1, the OS will complain, will give you, and then your program will crash. Okay. Now, if you are unlucky, maybe you have a value of 2004. And somewhere here you have an important variable, 2004. Maybe this is something important, let's say your age, something like that. And without initializing x to something, you are using the garbage value, which happens to be a valid memory address. And when you do star x equals to 1, you follow that pointer, you go to this valid memory address, you change it to 1, unintentionally. And these type of bugs are very difficult to catch because your program doesn't crash and the behavior is not deterministic. You run your program one time, suddenly your age becomes 1, then you scratch your head. Why? Then you try to run again, right? And because you're using uninitialized value, next time you run, the value might be different. Right? Now, next time you run, maybe the value is 3004, and then another variable will change without you knowing. Okay? So, the moral of the story is that if you use pointers, make sure you always initialize your pointers. Otherwise, your program is going to have very undeterministic bugs that is very difficult to catch. Okay. All right. So I will stop here for today. I'm going to finish the rest of the slides next week, and also I will talk about the answer to these two questions next week. All right. See you next week in the labs and tutorials.
Hi. I just registered for this class today. I'm